Don't do it.
So some questions have been asked, but please really feel free to ask questions in the middle. We'll have time for more questions at the end, but please don't hesitate.
All right, so let's get started to do some compositionality and recursive neural networks. So first I'll tell you a little bit about how we can apply recursive neural networks to parsing and learning these tree structures, and then give you just a very brief theory section on backpropagation structure. Fortunately, it is really very similar to the one we've already gone through, general backpropagation, so we don't have to spend too much time on it. And I'll talk about a variant of recursive neural networks, which is a recursive autoencoder. Again, fortunately, we're building on things that we've already discussed in autoencoders, so just applying them in the tree structure recursively. And then we can go on to applications on sentiment analysis, paraphrase detection, and others. All right, so parsing, I'm guessing most of you are familiar with it, but just in general, what would we like our parser to do? Well, given our sentence, such as the cat sat on the mat, and originally vector representations representing each of the words, we'd like the algorithm to first realize, well, the cat is a noun phrase, and those two words should be combined first. And similarly, the mat, and on the mat is a prepositional phrase, sit on the mat is a verb phrase, and so on. So that's sort of the general parsing task, and there has been a large amount of great work on it. But what we're actually more interested in is assigning a vector representation now for all the phrases in the parse tree. And that vector representation ideally will capture not just the syntactic information, but also semantic information about the words and how they're being combined. So how are we going about doing that? Well, essentially our major computational unit is a neural network, and its inputs are two candidate children's representations, or vectors. In this case, on, the vector for on, and the vector for the phrase the mat. And then there are two outputs. One is the semantic representation if we were to merge these two nodes, and two is a score of how plausible it is that we should be merging these two nodes. And so you might ask, well, how do we actually compute the score? And again, we're building on the techniques from part one. First, we just concatenate the two children vectors into one long vector. So if they're all two-dimensional, we'll have here a four-dimensional vector, 8, 5, 3, 3. And then we again apply a matrix, do a matrix multiplication, add a bias term, and then apply a nonlinearity such as the 10H. So that is essentially just a very standard neural network layer, such as we've seen before. And then in order to say, well, how good of a parent is this? Does it make syntactic sense to be combining these two? We again can use a similar idea as before in Paul Graham-Weston's word vector learning model, and just have an inner product here of a vector times this parent. So, and the reason why we're calling this a recursive neural network is that we're actually using that same W at every element of the tree. At every node of the tree is being computed with the same matrix W. And of the entire second part, this is like the most important equation. So if you have any questions about it, no. All right, that's great. Then that means Chris and Yasha have done a good job in part one. All right, so there's been some related work on this kind of idea that we introduced in ICML 2011. First, Jordan Pollack in 1990 introduced recursive auto-associative memories, which are kind of use similar ideas, but he originally worked with sort of these one-hot vectors, and so it wouldn't scale to very large vocabularies, and he assumed a fixed tree structure. And in our case, we actually want to learn the tree structure as part of the model and the vector representations. Costa et al. And Galler and Küchler also worked with recursive neural networks, but also in all cases assumed a fixed tree structure. Also, Hinton and Leong-Wu, Jeff Hinton, one of the sort of most important figures of deep learning, and Leong-Wu, they also had related ideas about recursive models and sort of recursive operators as smooth versions of logic operation and things like that. And we're actually going to tackle that at the very end of this part too, these kinds of ideas. All right, so how are we going to about parsing an actual sentence with a recursive neural network? I'll describe to you here a greedy version, but we can actually have more complicated sort of CKY-like beam searches too. But for just illustrating you the main ideas, we'll describe it as a greedy process. So what we'll first do is we apply that neural network to all possible pairs of words in a sentence. So we have the cat, we take its two vectors that we got from the previous model, pipe it through the network, compute a parent vector representation. And then we do that for cat sat, sat on, and on the, and the map. So now we have all these candidate parent vector representations, and we have the score of how plausible it was to merge these two. And what we'll do next is we just merge the two words that got the highest score. So in this case, 3-1 here has the highest score, so we merge these two words. And now we again we have a candidate that we want to compute, which is combining the phrase that represents the bigram, the cat, with sat. So again, we apply the same W matrix in the same neural network to compute another candidate parent vector representation of the score. And now notice how this would get a larger score because the cat sat is actually not an unreasonable syntactic phrase. But the mat is an even more obvious noun phrase, so we'll merge those two words next. And again, compute a new candidate for now merging on with the mat. And we can essentially continue like this up until we have the whole tree. So we can train this whole model in a max margin framework. So let's first define how well we're doing on an entire tree by just saying the score of one full tree is computed by the sum of the parsing decisions at each of the nodes. Yes?
Yeah, the previous slide. So when you look at the inner representation that left from the blue and bigger length, so what kind of crashing have you got? So for example, you got some representation for the tree. We're capturing the most ingredient from the.
So the question is, what kinds of things do we capture with that? And that's a great question, and I'll show you some examples of what we capture in about 2 slides. All right, so we define the score of the full tree as the sum of the scores at all the nodes. And then similar to max margin parsing from Van Tasker et al., we have a supervised max margin objective. So in this objective J here, which we want to maximize, it sums over all the training sentences xi and their corresponding given ground truth tree yi, such as ones from the Penn Tree Bank, the Wall Street Journal. And in the first part here is the score of the correct tree. So we have a sentence xi and its correct tree yi, and we want to maximize that score for each of our training samples. In the second part, we take the maximum over all possible trees of sentence xi, which we denote as a of xi. And of the one that receives the maximum score, plus the margin loss, which penalizes the incorrect decisions, we basically want to minimize that tree. And so the second part basically wants to minimize the score of a tree that is incorrect, but does in fact receive the highest score. And once the tree with the highest score is the correct tree, it's actually correct up to a margin, to the next highest scoring tree. And if y and yi are actually the same, then everything cancels out, delta is 0, and we're done with training that tree. All right. So I mentioned, you can see how we have here again a very well-defined objective function, and we just want to maximize that. And we can again use similar ideas, stochastic gradient descent, LBFGS. But for applying these ideas, we need to first take the derivative. And again, it's just like before where we did backpropagation, where we carefully took derivatives, we also do that here. But because it's now in a tree structure, we call it backpropagation through structure, which was introduced by Goller and Kirchler in '96. And so it's really the same thing as general backpropagation with 2 main differences. 1, we split the derivatives at each of the nodes, and 2, we sum the derivatives of the W's from all the nodes. What does that mean? All right, so you know how each parent is computed with its 2 children during the forward propagation to compute the parent vector representation. And so that means that now the errors need to be computed with respect to each of these 2 children. And that just means we split our derivative. We get this delta vector from part 1, you split it in the middle, and you put 1 into the left child and the other part into the right child. And the sum of the derivatives of all the nodes, you can actually, it turns out, you can assume that it's a different W at each of the nodes. When you sort of think back about calculus and how you took derivatives and things like that, you might think, well, now W depends on a function that depended on W and so on, and you might think it gets very complicated, but the intuition is really easy, and you can obtain it by just going through a very simple example where you take the derivative with respect to one W, and then you assume this is actually a different W at each of the steps of your tree, and it turns out the derivatives will be the same. And these equations are very simple, and you can go through them later. They're very similar to the equations we already went through in part 1. All right, so again, as I mentioned before, we can plug these gradients now into a standard optimizer like LBFGS. And you might be worried about this maximum here because this function is actually non-continuous, so it's kind of amazing, but you can basically use subgradient methods and still use SGD and other models to learn the weights W of these recursive neural networks. Just like before, where we had these multitask learning setups, we can also use the parent vectors that we now get that represent the longer phrase as features and input those into a softmax classifier. And again, just like before, the softmax classifier will actually modify what the parent vector representation looks like. And that we can make it sort of capture interesting things such as antonyms and sentiment and things like that. All right, so let's briefly go over some of the experimental results for using this parsing model. On the Wall Street Journal dataset on length 15 sentences, it actually obtains close to state-of-the-art performance and is comparable to some of the state-of-the-art parsers, such as the Berkeley parser. However, for longer phrases, there's still some more work needed in terms of how efficient these methods are. But what's more interesting to me is actually that we can now take these vector representations, map a bunch of sentences into that common vector space, and then look at nearest neighbors of that space, and that essentially answers your question, like what are we capturing with these vectors? And so what we did here is we just took the parser we trained on Wall Street Journal for parsing, and then looked at nearest neighbors. By essentially, given a set, such as the cats on a map, we compute this top parent vector representation. And then we can look at nearest neighbors to a specific target phrase. So if we pick the phrase, all the figures are adjusted for seasonal variations, then the next nearest neighbor in the space of these sentences is all the numbers are adjusted for seasonal fluctuations. And so that's kind of clear, right? Like, it's not that hard. It's just variations, swap of fluctuations, and figures and numbers. So you could say, well, that's kind of straightforward, and maybe you could swap synonyms and so on. But the next nearest neighbor is all the figures are adjusted to remove usual seasonal patterns. And you can see here that it abstracts from just the syntax and actually captures some of the underlying semantics too of these phrases. Similarly, if we have some company Night Ritter wouldn't comment on the offer, we take that as our target phrase, then the nearest neighbors of that phrase are Harsco declined to say what country placed the order, and Coastal wouldn't disclose the terms. So again, it's some company, but then you get some sort of negating word like wouldn't and declined, and then commenting saying disclosing. So it captures sort of both syntactic and semantic similarities. All right, so that's.
How does the model the least value or because you use LBFGS, then that's to go in one direction. So you value that maybe the initial representation also.
Right. So the question is, does initialization matter? And it turns out we actually initialize these word vector representations with the model we described to you in part 1. And that helps the model. It works like the best performance it gets when you initialize them with that, but you can actually also randomly initialize all the parameters and still get roughly the same performance. So initialization doesn't seem to matter too much. All right, so looking at nearest neighbors, just like topic models, it's kind of neat, but we also want to get some numbers. So the one task we applied this to was to try to do paraphrase detection of sort of short phrases. This was a problem motivated by machine translation. And we used here a data set from Chris Callison-Birch and one of his students, Bernard, who basically exploits sort of bilingual sentence-aligned corpora and hand-built linguistic constraints in order to determine whether a phrase is a good paraphrase to another one. And we simply reused our system that we learned from parsing the Wall Street Journal data set, and then looked at which one is the closest neighbor in Euclidean distance between the two vectors of a candidate and possible paraphrases. And we got a 22% improvement in F1 scores. And just to give you sort of a sense of what these look like, we can now have a target phrase, and then basically these were the candidates that the system gave us, and we want to now reorder them by our system. So this is just the reordering based on increasing Euclidean distance. And in parentheses, you have a human label of how good of a paraphrase this was. And you get a lot of sort of obvious things like around the world. The best one is around the globe. It would be